All right. Now, you can see this technique. This is what is called the feature-based localization. You have features, landmarks, and your sensor tells how many landmarks are around you, right? And your motion model tells your position and position of the landmarks, and the difference is used to adjust your position, right? So it is basically translation of the position linearly, and also rotation, and also scaling, right? So you need 4 parameters to bring your position as close as possible to the actual position. All right, 4 parameters, and these 4 parameters: tx, ty. That is the linear position change, and alpha is the rotation, and lambda is scaling. All right. So when you have 4 parameters, you need at least 2 landmarks. All right, at least 2 landmarks. Here you can see 3 landmarks, right? Just enough to run this algorithm and adjust your position. But if you don't have at least 2 landmarks, you are in trouble, because this technique will not give you enough accuracy. So that is one downside of feature-based localization. Now, there is another thing called featureless localization. If you don't have any features around you, think about indoor localization. Okay, so if you assume just a room with 4 walls and few doors, etc., you don't have any features, right? But what about the wall reflection? As you can see it over here, wall reflection. Can we use the wall of the room as features? If so, you can still use the same algorithm we discussed, that is feature-based localization. Okay. Now this illustration shows you uh, indoor localization, right? You can see the robot in the middle, and all these lines are LiDAR beams, infrared laser beams, right? And they hit on the wall, and robot measures the distance, right? You don't have to have all of these laser beams here. Maybe you can take every 10th, okay? You use the 0th one, then 10th one, 20th, like that. So undersampled set of readings. Now, if you remember the feature-based localization, you always need pairs: actual landmark, your measurement, this pair. So you cannot have um, a measurement coming from a different landmark and associate it with another landmark. If you do that, you are in trouble. That is why we were so careful to make sure that when you're pairing, right, actual landmark and measured landmark, you need to make sure that you are referring to the same landmark. Okay, right. Now here, because actual landmark is a point on the wall, right? And see, for example, any of these lines, right? You can see this um, this curly line here. Let's assume this is what you see, your measurement of the wall, and robot think wall is there, but the actual wall is like this, straight wall, okay? And there's an error. This is the measurement error. And you know your position is over here on the curly line here. And you can first assume that the horizontal line from that measurement point to the wall gives you the actual landmark. That point on the wall can be considered as actual landmark. Okay, this is the first impression. And down here, you can see 3 beams, right? Um, the points, the measured points are the measured landmarks. And if you drop a line vertically downward, it hits on the wall, and that is the actual reference point, okay, actual landmark. So you prepare these groups So how many pairs? 1, 2, 3, 4, 5, 6, 7, 8. 8 groups. You can go ahead and implement the feature-based localization algorithm we already discussed. Okay. Now, only difference here is that you don't have specific landmarks here, but you identify few points on the wall as your landmarks. All right. Now, when you do that, um, you need to make sure that you are hitting on the wall. You cannot have any other reflection and associate it with a point on the wall. No, you can't do that. You have to be absolutely sure that the point you are referring to is actually a reflection from the wall. Okay, right. Now, going by that logic, you can write down these equations. Say, for example, in your measurements, if you see a point has x coordinate smaller than a quantity, epsilon, it's a small quantity, then we know that this is actually coming from the wall, not from somewhere else. This is actually reflected off the wall because it's so close to the wall, right? Then take that as a point on the wall and make that x coordinate to 0, right? So like over here, uh, like over here. So you get um, you get this point, x is very small, right? And you change it to 0. And the reference point is 0y. Actual measurement is xy. Reference point, actual landmark is 0y. Okay, now you're pretty sure this is a point on the wall. The reflection comes from that point on the wall. Okay, right. So you have a pair. So xy and 0y. So this is the pair. Measurement, reference. Same thing on the other walls also, same concept. Now, you understood the point. But now you will realize if you look at this diagram here, creating the pairs like this, going horizontally to the wall or going vertically down to the wall is not very accurate. Why? Because you can obviously see that robot has to move not horizontally, not vertically, but together, right? In order to reduce the error, you have to reduce the x error, reduce the y error at the same time. So therefore, it has to go move at an angle. Therefore, your pairing that we discussed earlier is not very correct. Okay. The correct way is this actually. You can see it over here. This is the actual measured point. You have to move left. You have to move down also, right? Left and down. You're going at an angle somewhere over here, right? And this is your reference point. This is your reference point. Okay. All the other points are like that. You have to move x, y together. So the better way of making pairs is like this. You have xy point very close to the wall. Okay. You change your x by dx by 2. You see the small x coordinate and deduct half of that. And small y coordinate, deduct half of that, divide by 2. So now when you do this adjustment, you are actually moving at an angle, right? So this is a better way of making pairs, right? Compared with this one over here. For any small x, you just make it to 0 and y and use it as a reference. I think this is much better, right? This is much better. So reduce x, y, both coordinates, right, by half of that small distance to the wall. Then you can continue with the feature-based localization. Of course, in LiDARs, there are so many readings, but if you get maybe 20, 30 pairs, that's enough, equally spaced, okay? And this is the algorithm named as ICP, iterative closest point algorithm, okay? Iterative closest point algorithm. All right. Now, today, we are going to discuss a new aspect of robot localization. This is primarily after the work by Sebastian Thurn, and he published a book called Probabilistic Robotics. In that aspect, we consider the position of the robot as a probability distribution, okay? We don't say where the robot is, right? We don't know, but we say there is a higher probability for the robot to be in that particular location. And the robot position should be somewhere around that point. So let's look at the reality. For that, I want you to pay your attention to this diagram over here. So what is that? So we have a robot and we drive the two wheels with the same number of turns. Let's say, for example, the circumference of the wheels is, let's say, 100 centimeter. Okay, so one turn, 100 centimeter. All right, so you start at some point, let's say 0.0, and then turn 10 times, right? So that is about 100 centimeters. That is about 1 meter. So you assume that the robot's position is 1 meter, okay, about 1 meter from where it started off. Now you can take a ruler and measure the distance. Is it exactly 1 meter? Probably 1 meter, but maybe 99 centimeter or 101 centimeter. So this is what happens if you do that experiment. Okay, we can say, okay, there's a 50% probability that your reading when you measure the distance is actually 100 centimeters, but also it can be 99 centimeters with 25% probability, can be 101 centimeter with 25% probability. So when you add all these probabilities together, is 100%. Okay, so it can be 99, can be 100, can be 101. So I'm showing you three different possibilities with the most probable case being 100. In reality, your measurement can be 98, 97, 96 on this side, and 102, 103, 104, 105 on the other side. So then it becomes a bit more complicated, but it's still the same concept. Okay, so this is the probability of for the robot to be in that distance or that state. Okay, now after that point, after turning 10 times, okay, we came to a certain position, and now I ask you to do the same thing again. Turn the wheels 100 times, sorry, 10 times, right? And now you are here, 2 meter point, and you assume that now you are at 2 meters. Earlier 1 meter, now 2 meters. So how do we expand our probability graph, right, to the second state? This is how it looks like in the second state, or second event rather. If you stopped at 99 centimeter mark, right, from there, right, you would go another 99 centimeters or 100 centimeters or 101 centimeters. Okay, that is one possibility. But if you stop exactly at 100 centimeter in the earlier case, now you are going from that point to another 99 centimeter, 100 centimeter, or 101 centimeter. Or if you had stopped at 101 centimeter in the previous case, now from that point onwards, right, you can go in the second phase, another 99 centimeters or another 100 centimeters or 101 centimeters. Okay. So therefore, now there are 9 different possibilities getting your robot eventually to one of these positions: 198 centimeters, 199 centimeters, 200 centimeter, 201 centimeter, 202 centimeter. So any of these positions are possible. Now, how do we bring the probability calculation forward? Well, it is said by based on a base rule of conditional probability. You have one event, and on top of that, based on the outcome of that event, you have another process, right? Conditional probability. So you have to multiply these probabilities from previous case to this case, right? Considering all of these possible scenarios. Now, if you take this 99 mark after the first process, when you go to the second phase, it's very similar to the first phase over here, where you had 3 possibilities. Same 3 possibilities are here, right? Then you multiply these probabilities coming from 0 over here, 25% probability, and then this is also 25% probability. It is now as a fractional number 1 over 16 probability for you to be at 198 centimeters. I think you get that point. And all of these different possibilities, you can calculate the probability by calculating these probabilities along the tree graph, right? All of these possibilities. So this is what is called the conditional probability. You can see it over here, right? If you want to calculate what is the probability that you end up in any of these final outcomes, well, you have to multiply the probability of the first event, probability of the second event, okay, along that line, continuous line from 0. Now, finally, if you look at these numbers over here, you can see nearly half, that is 3 over 8 probability is there for the robot to be at 200%, 200 centimeter mark. This is your expectation, okay? 10 turns means 1 meter. Another 10 turns means another meter. So 2 meter. That is the highest probable case. But there are other cases also. So you can continue this for the next step, the 3 meter, 4 meter, 5 meter, 6 meter. Then you will see this becomes this is growing and it becomes out of control. And this is what is called the histogram filtering. Remember the word histogram filtering. Why? You can see over here the histogram. You can see the histogram here. After 1 meter, it looks like this. After 2 meter, looks like this. 3 meter, looks like this, like that. So, in fact, this is much broader than the previous one. This is the broadest. You get more and more bars, right, onto your probability histogram. So it's become wider and wider. The peak gets down. So when the peak comes very to the smaller height and it increases the width, which means is very uncertain where the robot actually is. It can be anywhere in a very big area. Okay. But if you see the histogram is narrowed down and middle one is highest peak, we know most probably it's there, right? So it cannot be any other place. It should be at that point or around in a very small area. So theoretically, this looks all right, very logical, right? We can implement because it's a tree, but the downside is this is not scalable in the sense the computational burden increases exponentially. So therefore, you cannot use this for any practical robot localization process. What shall we do? Well, if you look at the problem is this multiply and sum, multiply and sum, multiply and sum process, right? Sum of products, in other words. In mathematics, we call it convolution sum. Convolution sum, okay? You have to calculate each and every histogram and then add them together. That is where the computational burden comes. If you can have a mathematical curvature rather than the histogram, right? You can calculate the probability without calculating individual histograms, the bars, and adding them together, right? You can have one curvature to represent this histogram, and you calculate the probability in one equation. That way, it is very scalable, right? So that's why we want to bring in normal distributions. In fact, if you look at the normal distribution, it's very similar to histogram over here, isn't it? This histogram, right, when you have so many of these bars, it resembles in a way the normal distribution. So let me first introduce normal distribution to you. Maybe you have forgotten some of the basics by now. Before we get going, we need to understand what normal distribution is. So that's why I have this uh, content here. So on the left-hand side over here is normal distribution, okay? And on the right-hand side, this is the uniform distribution, right? You have done uniform distribution when it comes to, say, white noise, broadband noise. When you add noise in your simulation, this is what you do, right? Using a rand command, you can generate uniformly distributed sensor noise, whatever it is, right? When you do sensor fusion or Kalman filtering and that sort of simulations, you want to generate and add noise. So this is this distribution. So all of the frequencies, they have the same probability, right? Whereas in normal distribution, it's not the case. There is a mean value. It is 0 over here, but it can be negative and positive values to the left or to the right, right? At any value. For example, if I give you a multimeter, right, and a battery, and I ask you to measure the voltage, you measure it and get the reading, okay? Say 12 volts. Then I ask you, okay, do it again. Then you measure it again, 12 volts. Measure again, 12.01 volts. Oh, now it's a bit different. Do it again, 11.99, yet again different value. So likewise, I ask you to do this 1,000 times, 10,000 times, right? Assuming the batteries remains the same, right? Without discharging. You will get a graph like this. And I ask you to, okay, draw them, right, around 12. So whatever difference, 12 plus 12 minus, this 0 means actually 12. This is the error actually, right? How far off your measurement is and how often you get these off measurements, right? If it is exactly 12 volts, 0 error. If it is 11.99, is one error. 12.01 is a different error, right? So you will see this kind of graph. There are a lot of natural processes which agree with this particular distribution. Now in mathematics, this is that graph. E to the minus half y minus mu over sigma whole thing square. This is the normal distribution power density function. We call it power density function. You get this shape. And if you integrate from minus infinity to plus infinity, the answer is this one, sigma root 2 pi, the total area. So now you use that total area and divide the function by that value so that when you evaluate this one, the answer is 1. Okay. But you see 1 over sigma square root 2 pi is actually the total integral from minus infinity to plus infinity of the power density function. When you divide the power density function from that value, the total probability, and you integrate again, the answer is obviously 1, right? So that is to say that the total probability is 1. Entire area under the curve, the shaded area, is 1. Okay, if you use the power density function like this. Now, if you integrate from any point to any other point, right, around 0, you get some probability, and that is a probability of getting a reading in that area. For example, you can say, what is the probability in that voltmeter experiment that you get a reading from 11.9 to 12.1? 11.9 to 12.1. So you have to integrate somewhere over here, a small area, right? 11.9 to 12.1. So assume, let's say you get 60% or 0.6 as the area. We know 60% probability is there for you to get a reading between 11.9 to 12.1, okay, for a 12-volt battery. All right, okay. So I think you got that point. Now, what is the sigma here? The sigma is the standard deviation. And for this graph here, normal distribution, right? Sigma gives you 68.2 percentage centered around 0. Here it is 0. Here it is mu. Mu is the mean value. Okay, mean value. So 12-volt battery experiment, you are measuring it again and again and again. 12 is the mean value. 12 is the mean value. Mu. Okay. And standard deviation is whatever the value which gives you 68.2 percentage, right? Probability in your measurement. So you figure out what is that? Is it 11.8 to 12.2 or whatever? You can calculate sigma. Now, there's another example here. Example mu equals 0, right, over here, and sigma equals 1. Let's put these values here, right, to the probability distribution function. Now you can see it over here, y minus 1 over 1 square. So this 1 above is actually mu, right? So y minus mu over 1. This one is the sigma, right? So this basically mu equals 1 case, not 0 case, right? So you get this answer, 1 minus whatever it is, 0.9997. So 99% probability, right, for you to have this probability from minus 4 to plus 4. Okay, in that case, mu is 1. Right. So that's about the normal distribution. And this graph tells you some additional information. 1 mu is 68.2% probability, 2 mu is 95.4 percentage, and 3 mu 99.7 probability, and here you saw 4 99.97 probability, right? So it's about any measurement, right, being within any of these marks here, 68%, 95%, 99%, right? Um, that gives you how likely, right, your measurement being in these areas. Okay. So what you need to remember is this equation, probability density function, right? And when you have mu and sigma, just two parameters. Mu is the mean value, sigma is the standard deviation. All right. So when the standard deviation is broader, you're not very sure where you are. If it is narrower, you're pretty sure you are there at that point. Okay. Mu is that value, center value. So how likely you are there at mu is determined by sigma. So you can bring this concept to mobile robot localization to figure out where the robot is. So you need to find out your mu value. What is the mean value? Then you know, okay, robot's mean value is this 3 meters, 4 meters, 5 meters, whatever it is. And also you have to tell what is sigma, right? Sigma is the standard deviation. If sigma is, say, 1, now you know that the robot is at mu, but it can be 1 meter. If it's a line, one-dimensional robot, it can be plus or minus 1 meter, right? That gives you 68.2 probability, right? Let's say your mu is 50 meters, standard deviation is 5 meters. What does it mean? It means the robot, the probability of the robot to be at that location, that is 50 minus 5, 50 plus 5. That is 45 meters to 55 meter area in one line, okay? The probability that the robot is located in that range, 45 meters to 55 meters, is 68.2%. So you have more than half, in fact, 62% probability that the robot is between these two areas. Okay. Now, if you want to say the same thing in a slightly different way, you can say, you can go to 2 sigma point here, 2 sigma point, right? You can see it over here. You can say 2 sigma means 10 meters, right? Now you say this 50 minus 10, that is 40, and 50 plus 10, that is 60. The robot can be anywhere between 40 to 60 meters with a probability of 95%, right? Now you are giving more assurance in terms of probability, but less certainty. Now it is 40 to 60, right? Now, eventually, this is the reality of a lot of things, right? We cannot be very exact on anything, but we can say very clearly what the probability is and what is the range is, okay, from this point to that point. So this area is what is called the probabilistic robotics. All right. Any questions, please, about the normal distribution? And here I have a small numerical example for you to understand what is standard deviation, variance, mean, covariance, and also correlation coefficient. These things are actually coming in our way. If you do not understand them, you have problems understanding the theory I'm going to present to you today. Now here you can see two variables, right? let's say measurements, right? I give you a multimeter and ask you to measure a voltage, and you measure it, and these are the numbers, okay? Two batteries, let's say two batteries. One battery is X, the other battery is Y, like that. So these are readings 1, 2, 3, 4, 5, 6, 7, 8. Pretty easy to understand. The other one 5, 6, 8, 6, whatever it is, right? Uh, now, if you take only the X, your measurements, you add them together, divide by the number of measurements, summation X over 9. The answer is 5. That is the mean value. You know that, okay? What is the mean value of X is 5. Pretty easy. Now, I ask you to do this. You get the square sum. You square each and every X and add them together, divide by number of measurements, right? Square sum and divide by number of measurements. So this is the mean sum of squares. And then deduct from it the square of the mean, X bar, right? You have earlier calculated X bar. So the answer is 6.7, right? So this is what is called the variance. Now you get the point, right? This is what is called the variance. How widely or narrowly the numbers are spreading. Now, this is a square term, remember? It comes from squares. Now, when you get the square root of that, we call it standard deviation. Get the square root of this, and that is the standard deviation. Now, you can do this for y, variable y also separately. You get different numbers. You get the mean and the standard deviation. So, this is the variance, okay? Square root of this is the standard deviation. Now, create a mental model of the mu and sigma. Mu is the mean, that is over here. Sigma is the square root of this one. Okay. So together we communicate some very useful information about X, about the variability of X, where the mean value, how it is spreading around the mean value. For Y also the same story. Now, if you put these two together, you can get what is called the covariance. Covariance. Earlier, it was variance, okay, with just one single variable. But now, if you combine X and Y together in this format, you can multiply X and Y, okay, and put it in here. Now, this time, it is the sum of products, X and Y, divided by number of measurements, minus X bar, Y bar. Now, if you look at this one here, variance, you can see some similarity, because in case of variance, it is the same variable. But when it is covariance, you get two variables, right? X bar, Y bar. And when you multiply, it is X and Y. You bring mathematics forward and eventually get this 4.1. This is the covariance. This is the covariance, all right? When you say co, it means not the same variable, but two variables. Now, if you want to find out whether X and Y are related some way, because they are coming from the same process, even though they are two variables, you can do the correlation coefficient, or it is the covariance over standard deviation of X and standard deviation of Y. So the variances X and Y, their square roots means standard deviations, right? So you get 0.77. Now, what it tells you is that if this number correlation coefficient is closer to 1, right, they're very highly correlated, which means when X increases, Y also increases. When X decreases, Y also decreases. They're coming from same origin. If it is -1, out of phase. Out of phase means opposite. When X increases, Y decreases. It goes the other way, right? That is some sort of correlation, but it's a negative correlation. But if this is 0, which means they are not correlated. They are coming from different sources, uncorrelated. All right. So with that, we can come back to our localization discussion and try to apply some of these probability theories to find out where the robot is and what is the variability of the position. So any questions, please, up to now? Now you can see the same graphics here, right, that you saw earlier. I have my robot starting at 0 meters. Then I know pretty sure its location, 0 meters, because it has not moved yet. I know exactly the point where it starts going. That is my 0. I don't need any probability distribution here, right? Now, everything becomes a bit uncertain when the robot starts moving. So this is 1 meter position. I think it's 1 meter, but it can be 99 centimeter to 101 centimeter. You know that. And when it 2 meters, it can be 98, 198 to 202 meter. So gradually the uncertainty increases. Now, if you use, say, normal distribution function to express the position of the robot as you move forward, the probability distribution, because it gets wider and wider and peak comes down, at some point, your kth position probability distribution function and the probability distribution function of k minus 1 position might merge together because they are now too uncertain, too wide. So these probability distribution functions merge together. It can be, you can find yourself in this position, and when it comes to that point, it's highly uncertain. You have no idea where the robot is. It can be anywhere, literally. Okay. So therefore, there should be a solution for this. Now, this happens if you continue with your vehicle model without looking at your sensors, what the sensors tell you, right? Remember the probability distribution, how it advances from 1 meter, 2 meter, 3 meter, like that. So it's entirely based on your vehicle model, your wheel encoders, right? But if you incorporate the landmarks, you can, as we saw earlier, using some sort of similarity transform, you can adjust or correct your position. You can correct your position. In that case, this widening of the probability distribution can be controlled, bring it back to narrow probability distribution function and keep it like that as you move forward. So that is our approach here. How can we incorporate the measurements in order to reduce this width of the distribution function, the increasing width of the distribution function, or increasing standard deviation or variance? How can we control it, narrow it down? Okay. That is why we use what is called the measurement. All right. So let's bring in the measurement. If you look at the measurement part, right? Suppose there's a wall ahead of you and a robot has the LiDAR and it uses the beams and calculate the distance to the wall. Okay. And you get a measurement. How accurate is this measurement? Well, if you look at the manufacturer data sheet, they will tell you that it is also not 100% accurate, right? There's a distribution again. There's a distribution again. But most of these sensors are sophisticated, than wheel encoders, right? The wheel encoders, even though the encoder itself is very sophisticated, you are connecting it to a wheel that you make. And if it's a rubber wheel, you inflate it, or sometimes you don't inflate it so much, so your diameter changes. Therefore, the circumference of the wheel is not very certain, and also the width between between the wheels is also not very precise, and you have some measurement that also is an error. So therefore, your vehicle model has higher errors than your LiDAR sensor. So LiDAR sensor has errors, but not that much, okay, generally speaking. So we can draw it like this. This is the LiDAR error distribution around zero, right? You do the measurement, let's say um, 10 meters from the robot to the landmark or to the wall, but it can be 10.1 meter or 99.9 centimeters. Okay, so plus or minus a couple of centimeters is possible, and this is the distribution function. You can look at the data sheet and find out what is the standard deviation, and mean is usually zero. Mean is usually zero, which means if you use a equipment to measure something, the equipment is not supposed to add a fixed error to the reading, but the equipment or sensor has a noise, and noise is plus or minus. Okay, so it's around the measurement, but it does not add any fixed quantity to the measurement. Let's say when you measure your temperature using a clinical thermometer, right? It is supposed to measure the actual temperature with some noise. It's not supposed to add another degree or two to your body temperature or reduce a degree or two from your body temperature. No, there's no fixed error, which means there's no mean. Most of the sensors, some sensors, they might have this mu thing, but most of the sensors, by design, it is supposed to make mu zero. All right. Now, how do you incorporate the sensor measurement with your um, robot's probability density function, the position? Earlier, we saw that you can have this kind of probability density function for the robot, right? You can create it. The K here is the step. This is the mean value. How many meters away the robot is from your starting point, and the distribution. Now, given that probability distribution function, you do the measurement. So this is now again a conditional probability. You are not certain about your position, and wherever you are, you take a reading. Okay, using your wheels, you have calculated the probability distribution function of the robot's position, and that is not certain. That is why you have a probability distribution function in the first place. And now use your LiDAR to take the measurement. Now, let's say your LiDAR measurement is actually measure the distance from zero, right? To make it simple, does not have to be that all the time, but let's assume the same distance is measured by LiDAR, right? It's a one-dimensional thing. To make life easy, let's talk about one-dimensional thing. Robot is moving straight along a straight line, okay? Now, according to the Bayes theorem, this is how we calculate the probability density function, okay, using the measurement, So how it is done? Now, here you have Px. Px is the probability density function you have already achieved based on your vehicle dynamics. Okay. And now you have your, given the probability density function, you do the measurement. So the PZ comes in over here, given X, right? This is basically the probability density function of the sensor. And now you divide by Pz over here. So this is the total probability, Pz. As you can see it over here, it is the summation of all of these numerator probabilities. Add them together. When you divide by that number, you normalize it, because the total probability has to be 1. So to make that happen, you divide it by this summation. Now, in this diagram here is a bit more clearer than the equation. Now look at this one on the left hand side, right? So this is your Px, right? Using the wheel encoders, you have your probability distribution function of the robot, right? So it's at this point xb, and this is the peak, and this is the distribution, that is Px. And now you have your sensor telling you this one. So sensor tells you this is your actual position xa, and this is the distribution function for the sensor. Now the Bayes theorem says you have to multiply the two together, this probability with this probability. So for every value here, right, on the x-axis, you multiply the two probabilities. You don't do it manually, like in the histogram case. Now they are like probability distribution functions. You can analytically solve this multiplication process. But this is just to illustrate you, okay, what's happening. Then you know somewhere here, because both curves tend to 0 somewhere here, when you multiply the two together, it's 0. And also somewhere over here, right, even though the sensor distribution function has a higher value, the vehicle model based PDF is almost 0 over here. So when you multiply, the product will also be closer to 0 somewhere here. So therefore, this is the product, right? When you multiply the two probability distribution functions, this is what you get. So this is after correcting the position probability distribution, this is what you get. Now it is a bit narrower. Understand? It's a bit narrower. After this multiplication, it becomes narrower. This is exactly what we want to do. And also, the mean value has changed. Now it is a bit higher than Px, but bit lower than, sorry, xb, but lower than xa. So you adjust your position, most likely position, and also you narrow down the spread using the measurement. So this is what happens. On the other hand, if you look at this one over here, right, the top one remains the same. This is the vehicle model base position. And then in the middle, you can see PZ given X. That is the sensor probability distribution function. Now it is, let's say, a bit wider, a bit narrower somewhere over here, right? Than this one. When you multiply again, you get something like this. Now this time, the resulting probability distribution is not as narrower as in earlier case, but bit wider. So you still have some uncertainty in this particular case, second case. So the final remarks on this is as follows. You can use the vehicle model and predict your future position as a probability distribution function, and then you can bring in a measurement distribution function and multiply the two distribution functions and get the result. And this result will tell you your most likely position and also the spread. And if you have a better sensor, which has a smaller standard deviation, your prediction will also have smaller standard deviation. And going forward, you can maintain your standard deviation as narrow as possible so that you know more confidently uh, the, the most likely position of the robot. Right. So there are two basic equations here. What is that? One is the motion based one. You can see it over here, right? It is the convolution, right? It is the convolution. So you have your vehicle model based probability going forward in this format, okay? And at each step, you have your LiDAR measurements, and this is that, the measurement based correction of your position, okay? So there, the equation is slightly different. You get two probability distribution functions multiplied together, right, and divide by the total probability, the summation of all these numerator probabilities. Any questions, please, up to now? All right. Now, what we are trying to do here is to bring two probability density functions. They're both normal distributions multiply together, right? On one hand, the vehicle model, the other hand, the sensor model, okay? When you combine these two together, you get another distribution function, which is also normally distributed. So in one go, you can generate your location and standard deviation or variance without having that problem earlier. If you were to use the histogram distribution, right, the computational complexity increases, but now it's not the case. And remember these two equations, right? You use this one for the vehicle model to predict your future position. And also this normalization function, remember, 1 over this total probability to make sure probability, the total probability is 1 when you calculate, right? That is a requirement. And then the measurement model is like this. Again, there you can see the normalization function over here. All right. Yeah. Now, we need to understand what we are dealing with here. I want you to recall your memory on the state space model. State space model is actually a dynamic model. You can say a vehicle model here. When you know your previous state, you can calculate your present state if you know the control signal that is coming in, okay, control variables, 1 or 2 or many. So when you write down these equations, you have the state space model eventually. And in the state space model, there is observation, measurement also. Remember the second equation, y equals cz or cx rather, the output equation. So that is the measurement. So these are all connected together, right? To recall your state space model, the first equation is the vehicle dynamics. Second equation is basically the measurements, observation. Now, keep that diagram in mind. This is how we move from one state to another. we can use this information, this knowledge to calculate the future probability distribution function from a past probability distribution function. Because every step we have two processes. One is prediction using vehicle model. Second one, correction using measurement. We use two probability density functions each step. One is with P bar, which means it is the predicted probability distribution function using the vehicle dynamics. And then once you correct it, there's no P bar, there's no bar, it just becomes P. So in one state, let's say for example, state T, xt, right? You have Pxt. This is the final or corrected probability distribution function. And we say it, the belief after taking the measurement. Belief. We believe that the robot is in that position with that standard deviation after using the measurement, right? Now you move from Pxt to P bar xt plus 1. So time advances, and also there's a bar coming in, P bar. It is basically using vehicle dynamic model without correction. So once you correct it, you generate Pxt minus, T plus 1, similar to Pxt over here. All right. Now look at these two equations, 20 and 21. What do you see? This is P bar xt, right? So you have Pxt minus 1, the previous probability distribution function. And then in front of that, the state transition. This is xt, probability of xt given xt minus 1, that is the previous state, and ut minus 1, that is the control signal. This is primarily the state transition. So according to the Bayes theorem, you need to have your probability distribution function, right, that describe your present state, right, or maybe xt minus 1, right, as your previous state, and then multiply it with the probability density function that describe your transition. Okay, but what Bayes says is that the probabilities are multiplied every step. If you go through a sequence of events, all these probabilities are to be multiplied to get the final probability. So for when there are many possibilities, you have to do this for all of these possibilities and add them together. That is why you have the summation here. Okay. All right. So this equation gives you P bar xt. After collecting all of these different possibilities for xt minus 1. So xt minus 1 can be here, can be here, can be here, can be here, entire range. And for each and every possibility, there's a state transition, right, to xt once you give ut minus 1, the control signal. So you have to do this for each and every state, literally. Now, because we cannot do this computationally, now we bring in this nice analytical function so that you can do this multiplication and a summation as an integration in one go. That's why we bring in these probability distribution functions, right? Okay, so I think you understood equation number 20. What about 21? 21 is, okay, once you have P bar xt, you can see it over here. P bar xt. Right now, you know, using vehicle model and previous position, what is your likely possibilities now? So P bar xt, you know now. Now you get the measurement, right, from LiDAR. And for each and every possible scenario, right, you have to calculate your likelihood of your position based on your LiDAR. So that is the second one, equation 21. You can see this multiplication happening again. Okay, for each and every xt, you can see it over here. You calculate ZT, the measurement, again as a conditional probability. And also you have alpha here. Remember, alpha is the normalization factor. You have to have it to make sure that entire probability distribution, when you integrate, it adds up to 1. Okay, that's a requirement. So this base filter is it takes ZT, that is the measurement, ut minus 1, that is the control signal given at t minus 1, and the measurement is taken at t, and also pxt minus 1, the probability distribution function at t minus 1. So this is kind of iterative, right? Iterative process. Computationally much more efficient. So if we can implement this process, this is what we expect to get. The top one here tells you if you do not use the measurement, but continue with probability distribution function, histogram or normal distribution, initially you start with basically histogram, right? And eventually spread out, and it's of no use because you are not in a position to say anything about the robot's position. It can be anywhere. But now this one with the measurement, right, you will continue to keep your probability distribution function intact with a reasonable standard deviation, right, without letting it to grow too big. So this solves the storage problem, right? This again normal distribution function. I think I have explained this to you earlier. Remember this equation, e to the minus half x minus mu over sigma all things square. Mu is the mean or expected value. Sigma is the standard deviation. I think you know all of these things now. Now let's see how it happens. This is our first equation, 23. When you implement this process, you have pxt minus 1, as I explained earlier, probability distribution, in fact, a probability of pxt minus 1 at a given position, and multiply with this one, which tells you the transition from that position to the next position, right? And you have to integrate this for over all possible states, right? And that is why this integration is the equation 23. This is very much um, analogous to the histogram filter. That you can see it over here. Remember the tree structure going down, spreading all over. For each branch, you have to calculate, multiply, add, multiply, add, multiply, add. This is what you're doing here. You can see the multiplication here, two probabilities, and then add means the integration. The difference is now it is not a histogram, it is a continuous distribution function, so that integration is easy. So this is the prediction part. Prediction means using the vehicle model only, you can see it over here. This is the probability density function at t minus 1, right? Px t minus 1, it goes like that. So you have your position mu t minus 1. So this is what you say your position at t minus 1, okay? And there is a standard deviation, sigma t minus 1. Now, what happens? So this is the second part of the equation 23. Can you see it over here? Equation 23, second part, pxt minus 1 is something like this. Is normally distributed function with mu t minus 1 as the mean and sigma t minus 1 as the standard deviation. And the square of that is the variance. Now you multiply this with this one. What is that? This is the transition. Okay, this is the transition. So if you refer to the state space model, right, it's like this, isn't it? Xt is equal to a times xt minus 1 plus ut minus 1. You have the control signal coming in and state transition matrix A over here, right? This is a single dimension. If it's a multi-dimension, it's a vector or matrix. We know it. Now, with that state transition, you can say that your next mean from the previous mean would be this, isn't it? Because you know how it goes. This is a vehicle model, not anything else, right? If you stick to the vehicle model, this is your next mean. So that is why we have this second function over here. Again, a normally distributed function with mean axt minus 1 plus ut minus 1 over here. Based on the vehicle model, this is what you expect. So where you expect the robot be, right? After this transition. And also, what about your standard deviation? Well, your previous standard deviation is sigma t minus 1, this one over here. With this transition using this equation over here, right? Your new standard deviation is this one, mu, sigma r square, because this entirely the vehicle model, right? So vehicle model has some sort of process noise that is basically unmodeled dynamics, and it appears as a disturbance. We call it noise, but it's actually not the noise that we know of. It is basically unmodeled dynamics or disturbances and stuff like that to deviate the state, right, bit differently than what's happening through the state transition equation, this one, okay? So this is a new term coming up over here. So the standard deviation of the vehicle dynamic model is sigma r over here. Okay. So irrespective of the state you are in, whether it is k plus 1, k plus 2, it's the same vehicle. So same process noise is there. So you have to figure that out. What is sigma r? You can model it and find it out yourself. And you put it over here, sigma r. And you know that your transition from previous mean to new mean has this distribution with this mean. Can you see that? Axt minus 1, the previous mean previous state rather, times A plus ut minus 1. So entirely based on the vehicle dynamics, you can create this distribution function. It's entirely based on the vehicle dynamics. Now pay attention to equation 25 and 26. What are they? So the first equation over here is mu t bar. Bar means again prediction, okay, using vehicle dynamics. What is your next best position? What is your estimate? Right? It is equation number 25. Number 26 is what is your standard deviation? In fact, this has to be bar. Sorry about that. Sigma t. This should be sigma bar t square. Sigma bar. Bar means, as I said, before correction. Okay, before correction. Because of the vehicle dynamics, your mean and your standard deviation changes like this, 25 and 26. Right? You can see very clearly, control signal comes in, it changes your state, your mean, and the transition equation is here, A, because even you don't have any control signals, the dynamic model changes its position, right? The vehicle as it goes, even if you do not have any control signal or any gas, it will still go, right? Because it is self propelling to some extent because of the stored energy. So that is basically A, autonomous state transition. And based on that, A, the errors also change, okay? System errors depends on A. And this is the previous spread of the position, sigma t minus 1. And the process noise, that also adds something to the standard deviation, right? It makes a lot of sense, these two equations. And eventually you get sigma bar t square. Next, we go to equation number 24, that is the correction, right? Once you have this P bar xt, so that is the predicted probability density function at time t coming from this equation, right? After multiplying the two functions and the integration, you can put it over here. And this is the measurement model, P is at xt. So given xt, right, your measurement probability, right, probability distribution function. Now, if you look at the measurement, again, you can see it gives you the same mean xt, because sensor is not supposed to give a different mean, okay? Sensor is supposed to give you the same mean, but with some standard deviation. So therefore, you can say xt is in the middle, right? Mu t over here, and then standard deviation is sigma q. You have to get it from the sensor data sheet from the manufacturer. And your measurement, you said, as you know, in state space, the second equation is basically Z, right? The measurement is a combination of state variables, right? Z equals Cx. Sometimes we use variable Y instead of Z. But on the right-hand side, it is output matrix C times state vector X. So if there's any C, you have to put it over here, right? So this C should not be here. Z equals XC. So I will correct that. C has to go from here, right? It's not C Z, it's just Z. All right. So now you can see the two distribution functions for equation number 27. That is the correction. One of the functions is this one. You have mu bar T and sigma bar T, right? So mean and standard deviation after prediction. And this one is the measurement model. You have xt and sigma q. So there's no mean here, but there's a standard deviation. So we assume Z to be the mean here. This one is normally distributed around Z. Z is basically the measurement output. Okay. So it's also, we can say, xt, the new position. So both are same. Right. Now we bring equation 27 forward, right? And also, you know, this alpha is the normalization factor to make sure the total probability is 1. And then we continue over here, alpha times 2 probability density functions. Okay. Now we can write down the two probability density functions like over here, the second equation. Pay attention to the highlighted rectangle. The second one is P bar xt. Can you see the probability distribution function, right? Not normalized, the function itself, e to the minus half x minus mu bar over sigma bar square. So that has the mean mu bar and standard deviation sigma bar. So this is predicted probability density function. All right. Yeah. Then in front of that, you have another probability distribution function, e to the minus half Z minus Cx over sigma q, all things square. So which means now Cx is the mean because the measurement is like that. Measurement takes C times X, right, after state variables. And the standard deviation sigma q, you have to find out from the manufacturer's data sheet. And they both have normalization factors. And to normalize the whole thing, we can add another constant here, like alpha square. This is not the same alpha earlier, but this alpha star dash is also doing the same function to normalize the probability distribution function after multiplying the two PDFs. Okay. Now, in this equation, we are trying to combine them together. Can you see that? E to the minus half, you add the two exponents, right? And as you know, when you multiply two probability distribution functions, it also becomes another normally distributed probability density function. Earlier we saw in some graphics, two PDFs multiplied together, result is also a PDF. But here you have the mathematical description for the same. So I would write it like this initially, right? E to the minus half n times x minus r square plus m. So I bring in these three variables here or parameters n, r, and m, right, as the resulting normal distribution after multiplying the two functions. Okay. Now, how do I calculate n, m, and r? Well, if I have a quadratic function, remember these normal distributions, the exponent is a quadratic. Okay, can you see that? Z minus cx square, x minus mu square is squares, right? It's quadratic. So if I have this half n x minus r square plus n, this also is a quadratic function, right? How to find n, m, and r? Well, in this quadratic function, I can draw it like that, right? And minimum is actually m, what you get over here. And the value of the independent variable where you get the minimum is actually r. Okay, so r is over here. N is the normalization factor, isn't it? N is there to make sure the entire function total probability is 1. So that is sigma square over here. Can you see that? Sigma square over here, right? Because half is already there. You can see the half here. So to find out these things, these three parameters, you can differentiate the quadratic function with respect to the variable of the function, right? Partially, and set it to 0 like that. When differentiate, it becomes n times x minus r, and you set it to 0, and you can find x equals r. And that is the mean. So this is the mean in a quadratic function. The minimum value is the mean value, okay? So this r is the mean value. All what you need to do is to differentiate with respect to the independent variable and set it to 0 and solve that equation, and the result is the mean. If you do the partial differentiation again, right, what will happen? You partially differentiate this again, and the answer is n. And of course, we know n is there, right, in place of sigma square, 1 over sigma square, right, in this equation. Any of these equations, you take that one, 1 over sigma square, right? That is in place of n. So the moment you know n, n means 1 over sigma square. So which means you know the standard deviation. Okay. Now, if you have the quadratic function in the exponent, by differentiating it twice, you get the mean of the distribution and you also get the standard deviation of the distribution. You just need to differentiate with respect to the independent variable twice. So shall we do it for what we have here? So this is the function we have here. Two PDFs normally distributed multiplying. And you see the exponent, take the exponent, differentiate with respect to x twice, figure out the mean and the standard deviation, and you know the resulting PDF. So let me take this highlighted part over here, exponent, and write it as gx. This is the function I have now. I want to find out a single normally distributed PDF for this one. So what I do is, just by looking at it, I can say m is 0. I can say m is 0. There's no m here, right? What is m? M is this constant value. M is 0. There's no such thing in gx. Okay, that's fine. Differentiate with respect to x. Then this becomes like this. Second term becomes like that. Now we want to set it to 0. Set the whole thing to 0 and solve for x. This is the result. What we have solved here, that is for x, is actually the mean of the new probability distribution function, probability density function. You have just found out the new mean, corrected mean, or corrected most likely position of the robot. Equation number 30. Okay, so what's in there? You have sigma bar square, that means the predicted variance, okay? And you have sigma q, that is the variance of the sensor, and also z, that is the measurement, okay? And also c, that is the output matrix, okay? If it is just a single variable function and you directly measure the distance, you don't need c here. In fact, c would be 1, just 1, okay? You can uh, replace c with 1 if it is the case. Next, you want to find out what is my spread, okay? How confident I am with that mu, okay? Where is my robot, right? It is some value, but there's a range. So I want to reduce this range as much as possible. That is, I want to find out standard deviation. So for that, I differentiate this again with respect to x, right? Equation 29, you can see this one. Differentiate again with respect to x, then you will get this equation. Okay. So this is the 1 over sigma square, the new standard deviation, right? So if you get it inverted, you get equation 31. This is the corrected standard deviation. So equation 30 is the mean, 31 is the standard deviation. So you are done, right? At time t, now you say, okay, I know my mean, most likely position, and I know standard deviation. Now, if you now combine 30 and 31 together, in fact, you can actually substitute uh, for equation 30, right, from 31. So in 30, you can see c square sigma q square, the denominator, right, is same here, same denominator. So it's a 1 over denominator, right? Sigma square. You can bring it over here, sigma square times the numerator here. So this is your new mean. Now, isn't it very elegant, right? You can see mu bar, that is the previous predicted mean. And now with Z, that is the uh, sensor measurement. Sigma q is the standard deviation of the sensor, right? And you combine them together with sigma square, right? That is the new standard deviation, and you get the mean. If you want it to be in this shape, of course, right? Otherwise, 30 and 31 will explain the entire process. Is everything clear up to now? Now, why we write equation 32 here is not because it's the 30, 31 are not adequate, but it's for something else, right? So look at equation 32, where you write the mean value of the robot after correction, right? Using the standard deviation. Now you're combining standard deviation and the mu, right? Mean together in one equation, 32. And next step, what I do is I add and subtract c times mu bar. You can see it over here. Add and subtract. Doesn't make any difference, right? To Z over here, right? I keep C aside and take Z and then subtract C mu bar. So they're both mu bar. Okay, here you can see the bar and see the bar. It's actually bar, right? Uh, there's also another typo. I'll make that correction. Then you rearrange the terms as you can see it over here, right? Z minus C mu bar, one of these things go here. The other one is C square mu bar. It comes to the other side like this, C square mu bar with RQ square, the denominator, right? So after that, this whole thing can be written as C square over sigma Q square plus 1 over sigma square. It's not Q here, it's bar, right? So I will make that correction again. Sigma bar square, all right? Now, so that one is equal to 1 over sigma square. Earlier we have seen that, didn't we? Look at that one. Equation 31. Okay. So this is equation 31 basically. 1 over sigma square. So this sigma square cancel out, leaving only mu bar here, right? So therefore, we can write the equation as follows. You have sigma square over sigma q square, right, times CZ. Sorry, C can go out as well. Z minus C mu bar plus mu bar, right? So which means this turn out to a different format now, right? Which says there's a constant here. So sigma square is the standard deviation now, and sigma q square is the, sorry, variance. Sigma q square is the variance of the sensor. C is the output matrix or vector, or simply 1 if it is a one-dimensional thing and you have the direct measurement of the state without any conversion factors, okay? So it's a constant. At that moment, you can think of it as a constant, but it's not actually constant. It's changing all the time. It's kind of gain, varying gain, okay? Not a constant gain. It's a varying gain. And then you have this expression Z minus C mu bar. Again, if you forget this C thing for a moment, Z minus mu bar. So what is Z? Z is the measurement. What is mu bar? Mu bar is the predicted state. Going through your vehicle model, you predict your next position. Prediction. Z is the measurement. So measurement and prediction, there's an error. So you get this error, multiply it with a gain. We call this gain Kalman gain, and you add it to the previous the predicted position, mu bar. Now, this tells you a very nice story of sensor fusion, okay, or prediction and correction process. You have prediction process that gives you mu bar, your position, most likely position, and you have the sensor telling you this is your position. There's a difference between the two, and you have the Kalman gain to multiply the difference by that amount and add that to the predicted value. So this is the correction process. It's a very elegant equation, isn't it? 34. After all these mathematics, this equation is very simple and it makes a lot of sense. Right. So in 1D case, right? And now if you think k as 0, for example, right? K is 0. What does it mean? If k is 0, mu equals mu bar. What is that? Mu bar is your predicted position and mu is your corrected position, right? This mu bar uh, uh, was derived entirely based on the vehicle model, right? So let's say your sensor is very, very bad. In that case, you completely rely on the vehicle model. This is that scenario. Okay. When k equals 0, that's the case. So what is the reason for k to be 0? And if you look at this equation, this is k. For k to be 0, you need to have sigma q very high, isn't it? When you have sigma q very high, gain is nearly 0. Sigma q very high means your sensor is very bad. Sensor has very huge standard deviation. In that case, equation 34, simply disregard the measurement and rely on the vehicle dynamic model. Okay, so that's one option. The other one, when k equals 1, mu equals z. So what is that? When k equals 1, if you look at this equation, right? K1 means z minus c mu dash plus mu dash. So basically this c mu dash and mu dash, they are equal. As I said, in one dimension, c is, you can assume to be 1. So minus mu bar plus mu bar cancel out. The answer is z, which means you have a very good sensor. You have a very good sensor. So you disregard your vehicle dynamic model and rely on the sensor, right? If your vehicle dynamic model is bad, a lot of process noise and all that disturbances, unmodeled dynamics, right? Your state transition equation doesn't say anything significant to you, right? In that case, you can totally rely on your sensor. Put a sensor, read it, and use it as your position. All right. All right. So I think it's time for today. Any questions? Okay. In that case, we'll wind up for the day and we'll continue from this point onwards next week. Have a good evening.
In dynamics lecture number 2 slide, the PDF is not uploaded. I think only one PDF.
Oh, okay, okay. Right. I'll upload that. Thank you. Anything else?